Okay students, so this is the final lecture on the least squares portion. So today we're going to talk about some variants of least squares. Okay, the standard least squares problem, as we said, is just minimize ax minus b whole square. When a and b are given, minimize over all x. Right. We're going to look at three different variants. The first one we're going to talk about in some detail is multi-objective least squares. Okay, so here the idea for this least squares is that there is only one objective. This is your error, right? And you want to minimize your error, the error of how far b away is from ax. Okay, but in many scenarios you may have more than one objective. For example, if I were to call this objective g1 of x, okay, there could be another objective g2 of x that I am simultaneously trying to minimize. For example, I would like ax to be close to b, but I would also like, for example, cx to be close to d. Okay, so maybe this is another objective as well. Okay, so I want ax to be close to b and I want cx to be close to d as well, because I have two objectives that I want to achieve. Okay, that becomes a multi-objective problem, right? And when each of those objectives is a least squares expression, or linear least squares expression, then we call it multi-objective least squares. Okay, so how do we deal with multi-objective problems? Because there's not just one objective to minimize now, but you have many objectives, right? The standard technique is to take a weighted combination of the two objectives, lambda 1 j1x plus lambda 2 j2x. Okay, so I'm assuming that both these objectives are to be minimized. Okay, it's not like I have to minimize one objective and maximize another objective. This is common, for example, in portfolio trading. Let's say you have to decide how much to invest in each stock. Okay, so as is the issue with share markets, your returns will be random. Okay, so there's no guaranteed return. You have some expected return, but you have some variance on top of it, some plus minus something. Okay, so there are two objectives there. You might want to minimize your risk, meaning your variance, or you might want to maximize your expected gain. Okay, there are two objectives there. One of them needs to be minimized, the other one needs to be maximized. Here I'm assuming both of them need to be minimized. That's very easily adjusted. Suppose if this is an objective that needs to be maximized, right, then I can just put a minus in front of it. Then it becomes an objective that needs to be minimized. Okay, so fine. So let's assume j1 and j2 are both objectives that need to be minimized. I construct a weighted combination. Right, this becomes a single objective now, right? And I'll pick lambda 1, lambda 2 are the weight factors, the weights, right? Lambda 1, lambda 2, needless to say, must be non-negative, okay, because I'm going to minimize the overall objective. Okay, so that's what we'll try to do. We'll try to minimize a weighted objective. Okay, now lambda 1 and lambda 2 represents the relative importance of the two weights. Okay, I'll try to minimize this objective over x. Okay, now one important thing, one immediate thing to note is that slightly trivial, is that I can actually just take lambda 1 common, right? And since minimizing this whole function is the same as minimizing without the constant, I might as well get rid of the constant, right? So I can, instead of writing this, I could simply have written j1 of x plus lambda j2 of x. Okay, minimize j1 of x plus lambda j2 of x. Okay, so lambda is now the relative weight factor. So lambda has to be greater than or equal to 0. Okay, lambda is the relative weight factor. So if lambda is 0, then I'm giving importance to only the first objective. I'm basically ignoring second objective. Okay, and if lambda is infinite, I'm ignoring the first objective. Okay, basically the weight factor lambda decides. If lambda is small, I'm giving more importance to the first objective. If lambda is large, I'm giving more importance to the second objective. Okay, so this is how you would solve a multi-objective problem in general, nothing to do with least squares as yet, but multi-objective problem, this is how you would solve in general. Okay, the value of lambda is now a tunable parameter for you. Okay, so lambda is a parameter. Okay, picking different lambda will give you different result, because small lambda, as I said, favors the first objective, large lambda favors the second objective. So depending on which lambda you pick, you'll actually get a different optimal. Okay. In this context, there is a term that's often used that I would like you guys to familiarize with. So let us say that I solve this optimization problem and I obtain for each lambda, and I obtain the optimal value J1 star and J2 star for each lambda. Okay, and I take J1 star on this axis and J2 star on this axis. Okay, so let me just try to plot what these points would look like. Okay, so basically what I'm trying to do is I'll pick one lambda, then I'll obtain the I'll solve this optimization problem and I get the corresponding J1 star and J2 star. Okay, that gives me 1 point on this plane. Okay, maybe I pick a different lambda, that gives me a different point on this plane. Okay, so I have a set of all these points and I'd like to see what happens to the curve, to the resulting curve when I connect all these points. Okay, let's just see what happens when lambda equal to 0. When lambda equal to 0, I'm ignoring J2, right? So lambda equal to 0 is the region where J1 will actually be a very small value, but J2 may actually be very, very large. Okay, so that would correspond to some points here, right? So this would be the points you would expect here to be the low lambda region. Okay, so low lambda points. Okay, if lambda is small, then as I said, J1 will be optimized. That means J1 star will be small, J2 star may not be that small, so you will actually get points here. Okay, similarly, if lambda is large, you will actually get very small J2. That means J2y, this vertical coordinate will be small, horizontal coordinate may be large, so you will actually get points like this here. Okay, so in general you would expect some curve like this. Okay, this would be the high lambda region, this will be the low lambda region. Okay, okay, so when you draw such a curve, what's the important point is that you are never going to be able to get, no matter what lambda you pick, any point in this region. Okay, you are never going to be able to get any point in this region. Why is that? You are never going to be able to achieve any of these points. That's because, let us say I want to achieve this point, right? That means there should be a value of lambda for which I get a y coordinate, okay, and an x coordinate, both smaller than, okay, the corresponding y and x coordinate for that lambda. Okay, for example, so let's say there is a point here, and this point is the optimum J1 star and J2 star corresponding to that particular lambda. Okay, then to achieve this point, I should have had both a smaller x coordinate, meaning a smaller value than J1 star, and a smaller value than J2 star. Okay, because remember, this point is to the left and below this point. Okay, this point over here is to the left of this point and below this point, meaning it has a smaller x horizontal coordinate and a smaller vertical coordinate. Okay, so this point over here has a better first objective and a better second objective. Okay, that means that it has a better weighted sum. Okay, but we are already plotting the optimal points here. Okay, so if this point was achievable, then this point would have been on the curve. That's what I'm trying to say, right? So this curve is called Pareto optimal curve. Okay, the main idea behind Pareto optimal curve is that it's impossible for you to improve one objective without sacrificing the other objective. Okay, so if you are a point on the Pareto optimal curve, the only way to improve, let's say, the first objective, that means the only way to reduce J1 star is to actually increase J2 star. Okay, so it's impossible for you to achieve, if you are on the Pareto optimal curve, it's impossible for you to reduce both the objectives from there on. Okay, so that's the main idea behind a Pareto optimal curve. So in general, when you have, it's also possible to have more than two objectives. Of course, you don't need to have only two objectives. If you have more than two objectives, then you'll have more than two parameters, right? For example, you'll have j1x plus lambda 1 j2x plus lambda 3 j3x. Okay, this is lambda 2 j2x. So now the terms lambda 1 and lambda 2, well, once again, I think it's better to just, write this is lambda 2, lambda 3. Yeah, lambda 2, lambda 3 control the relative weights, relative importance of these objectives, and here you will get a Pareto optimal surface. Okay, fine. This is a general concept, optimization, related to optimization, not related to least square specifically, right? But I just thought I need to mention that because this word keeps coming up a lot. Okay, so let's go to least squares now, right? So what if you have a two objective least squares problem? Okay, so you have something like a1x1 minus b1 whole square plus lambda times a2x, so x1 here, a2x minus b2 whole square. So what if you have something like this? How do you solve this least squares problem? Okay, so well, if you look at the structure of this problem, well, remember how did we solve the least squares problem, right? We had many different approaches. We had geometric and whatnot. One of them was to actually expand it and recognize that this is a quadratic function and you know how to minimize it, right? Now what does adding a second term do here, right? It doesn't really change anything, right? This is a quadratic, this is a quadratic function. You add them, you still get a quadratic function. So this whole thing is again a quadratic function. So the same tricks and techniques should apply even to this, right? But what we will do is we'll actually try to write this down in a slightly better fashion. Okay, so what I'm going to do is I'm going to take this. So this is the norm of one vector, this is the norm of another vector. What I'm going to do is I'm going to put these vectors as two different coordinates. Okay, so I write a1x minus b1, okay, and 1 over square root lambda times square root lambda times, not 1 over square root lambda times square root lambda times a2x minus b2. Okay, so I have constructed a block vector here, right? So this itself is a vector and I have concatenated another vector on bottom of it. Okay, now the whole reason for me for doing this is to recognize that the Euclidean norm of this is actually going to be this objective over here, correct? Because when you take the sum of squares, right, we'll take the sum of squares of these coordinates, will give you this. Sum of squares of these coordinates will actually give you this. Okay, fine. So now let's try to see if we can write this objective as a matrix times variable minus no. Okay, so this objective can be written as a1 square root lambda a2 multiplied with x minus b1 square root lambda b2. Okay, so you see what we are doing here, we are trying to do here is we are trying to combine both these objectives under a single norm. There is a square here, of course. Combine both these objectives under a single norm. Okay, so this is what you will get. Now if you call this matrix as a tilde and this vector as b tilde, you have your standard least squares problem in a tilde and b tilde. Okay, so a multi-objective least squares problem reduces to a single objective least squares problem. Okay, fine, with a tilde given by a concatenation of a1 and a2, the corresponding matrices. There's some scale factor here corresponding to whatever factor you pick, okay, for lambda. Okay, so this a tilde x minus b tilde whole square, that's what you will get. And now you can solve this using your standard technique, right? So you can actually compute a tilde transpose a tilde inverse a tilde transpose b tilde. That will give you the solution to the multi-objective least squares problem. Okay, depending on what lambda you pick, you will get an answer. If you want to repeat with a different lambda, you just do it, reconstruct it. Okay, fine. So some very simple questions here. What guarantees that So remember, for these least squares problems, we've been saying that it is desirable that the matrix has full column rank, right? So what guarantees that A has full column rank? So if you see this structure here, well, for A tilde to have full column rank here, we need this matrix to have full column rank, right? This matrix to have full column rank is actually easier to ensure than ensuring that A1 and A2 have full column rank, right? For example, if A1 has full column rank, right, the columns of A1 are independent, then the columns of this full thing are going to be independent. It doesn't matter whether the columns of A2 are independent or not. We discussed this in the first segment, right? What happens when you concatenate, what happens to the rank and things like that, right? So if the columns of A1 are linearly independent, that's actually enough to make the columns of this full thing linearly independent. Okay, so A2 can be whatever, even the columns of A2 don't have to be linear. So it's much easier to make this whole thing full column rank than the individual pieces. In fact, A1, A2 can have linearly dependent columns, but on concatenating them you can end up getting independent columns. For example, A1 could just be like 1 1, A2 could be like 1 minus 1. Okay, as you can see, so A1 is just like a row vector. As you can see, both A1 and A2 have linearly dependent columns, but when you put them one below the other, you actually get a full rank matrix, right? So that can actually happen in this context as well. Okay, so you can do a very similar complexity analysis and all that stuff for the matrices here as well, right? So one thing is, you can actually write an expression for this A tilde transpose A tilde inverse, right? So that's actually going to be square root lambda A2 transpose plus A1 transpose, A1 transpose multiplied with rewrite this. So it's going to be A1 transpose square root lambda A2 transpose multiplied with A1 square root lambda A2. Okay, this quantity over here is A tilde transpose, this is A tilde. Okay, this is square root lambda as well. Okay, so if you expand this, you will actually get A1 transpose A1 plus lambda A2 transpose A2. Okay, so as you can see, the gram matrix of A tilde is actually simply a combination of the gram matrices of A1 and A2. Okay, so you can actually compute the gram matrix of A1 and gram matrix of A2 and store them, and for different values of lambda you can just add these two matrices, right? Fine. So if you want to repeat your multi-objective least squares problem for different lambda, all you need to do is add these two stored matrices for the different weight factors and take the inverse, assuming you're going by the naive approach, and then you multiply with A tilde transpose B tilde. Fine. So that's your multi-objective least squares problem. Okay, we can solve it even when there are more than two objectives. All that will happen is you will get a concatenation of more and more matrices here. So A1, A2, A3, A4, of course with different scale factors. Okay, fine. So let's look at some examples where multi-objective least squares would arise. Okay, so let us say that you are looking at to use a very simple example. Let us say I am looking at an image deblurring scenario. This example is from your textbook. This is chapter 15 from BMLS. Okay, so let's say we are looking at an image deblurring problem. Okay, so what is an image deblurring problem? So let's say X is your image, right? And you have you have Y equal to AX plus B. Okay, where this A is some blurring operator. Okay, so Y equal to AX. A is some blurring operator that has been applied on the image. Okay, and Y is what you observe. Y is the blurred image. Okay, this is a very standard signal processing problem. I'm not saying that the solution that we're going to give here is like the best solution. It's traditionally the standard example given, right? This V here is some noise. Okay, this is some blurring operator. Okay, X is the unknown, like in some sense the pristine image, okay, or the untampered image. Okay, I want to find X. Okay, I know Y, I have access to the blurred image Y. I want to find X. Okay, I don't know what V is. Okay, I want to find X. Okay, all I know is that V is possibly small. Okay, noise is not too much, noise is maybe overall very, very small. That's all I know. Okay, so there will be more sophisticated ways people will model this, and that I will leave for the end of this lecture. But for now, very simply, what I do know is that y equal to ax plus v. So I know that y is close to ax. Okay, y is close to ax. Okay, so now I want to find x. Okay, now the blurred image and the pristine image may be same size. Okay, so this A may actually be a square matrix. Right? But blurring operators or square matrices will generally be non-invertible. Okay, that's because blurring will lead to some loss of information. Right? You're destroying the sharpness in the image. Correct? When you do blurring. A more technical way of saying that would be you're destroying the high frequency content in the signal. Okay, so you're destroying the high frequency content or the sharpness in the signal, which means that this matrix is actually killing something, destroying something. It means it has a non-zero null space, which means it's non-invertible, right? Intuitively speaking, this will be a non-invertible matrix. So I can't simply write x equal to A transpose Y. That will be bad on many levels. First of all, A inverse will not exist, and even if it does, it may actually be very poorly conditioned, and remember the noise factor here that could potentially get amplified. Okay, so what should we do here, right? So I want y to be close to ax, but here is where A is not invertible. Okay, there could be many x that make y close to ax. Okay, there could be many x that make y close to x. Which of these x do I pick? Okay, so this is classic what is called an ill-posed problem. Okay, an ill-posed problem is a problem doesn't really have a unique solution. Well, I can't give an answer to this question, right? I mean, well, there could be many x for which y is close to x. Well, there could have been many images, right? Blurring has killed some content in the image. There could have been many original images that could have led to this blurred image. Okay, so a classical technique of dealing with an ill-posed problem is to do something called a regularization. Okay. A very basic level, what regularization is imposing some assumptions on x using some knowledge on the original x that you have. In this case, for example, maybe I do know that the pristine image x is smooth. Okay, maybe I know that x is smooth. So remember when we discussed the beginning of this segment, we said one way to quantify smoothness, if we had a vector, okay, smoothness would mean that the vector doesn't change from one coordinate to the other. So one way to quantify smoothness would be to construct the square difference term, right? x1 minus x2 square plus x2 minus x3 square plus so on, plus xn minus 1 square. Okay, like that, right? So basically x is smooth means an expression like this would actually be very small. Of course, x is an image here, so it's not very straightforward. You have to actually impose smoothness along both the horizontal direction and the vertical direction, for example, right? But for simplicity's sake, let me just take this to be my smoothness term, right? So what I want is, I want y to be close to ax. This is my objective one, is make sure that I'm actually getting the original image, right? The second objective is not very specific to the observed data y. It's not specific to y. It's just saying that x is smooth. Okay, meaning this expression here is small. Okay, for x. So you have two objectives here. One objective is y minus ax whole square. Okay, x is a variable. I try to pick x such that this is small. Okay, the first objective. The second objective is I try to pick x such that this quantity is also small. So you have two objectives here that you're trying to play with. Okay, this technique is called regularization. So regularization is just a technique of imposing your assumptions on the data. Okay, fine. So there are many kinds of regularizers that you could use depending on what knowledge you have or what reasonable assumptions you can make on the unknown x. Okay. A very popular regularization is obtained when you are trying to find a solution to ax equal to b, okay, that has small x, small norm. Okay, so remember the min norm solution we had is a typical case of this. You are trying to minimize among all solutions of ax equal to b, you are trying to minimize x, the norm of x, right? To norm of x. But here, actually, I don't care if ax is equal to b. I want ax to be close to b. I don't care about it being exactly equal. Like in most practical scenarios, because you know that there will be noise, I want ax to be approximately b, close to b. Okay, but I want x to be small as well. Okay, so this becomes my first objective. J1 of x, the first objective, is norm of ax minus b whole square. J2 of x, the second objective, is norm of x whole square. Okay. In that case, the joint objective, combining these two, will be something like this, plus lambda norm of x whole square. Okay, this is called the Tikhonov regularization. Okay, it's a very popular first-hand regularizer. If you want to solve a system of equations, right, but you are worried that there will be many possible x that will minimize this, then you will add this term over here. Okay, this term will ensure that you are actually trying to pick an x. So first thing to remember is any solution to this, meaning any x that minimizes this, may not actually satisfy ax equal to b. Okay, it will not actually, in general, it will not satisfy ax equal to b, but it will make sure that ax minus b is small and x is also small, depending on what lambda is, right? If lambda is very small, you may end up actually making ax equal to b, right? If lambda is close to 0. If lambda is very, very large, ax can be very, very far from b, but you will make sure that x is very small. The norm of x is very small. Okay, so once again, it's the relative importance of the objectives being played with here. Okay, fine. So if we actually apply, this trick here, okay, to this matrix, right? So here you had a1 and a2. In our case, a2 is just identity and b2 is 0, right? So remember, the second objective is just x, right? So it's as if a2, the term multiplying here, is identity and b2 is 0, right? So the objective here, a2, this becomes identity, right? So what you get here is the solution to this problem. You can easily check is A transpose A plus lambda I inverse A transpose B. Okay, this is what is going to be. Okay, so note the difference from standard least squares. If you don't have the Tikhonov regularization, you won't have this term. You will just have A transpose A inverse, right? But with the Tikhonov regularizer, you will actually get lambda I inverse. Okay, so lambda is sometimes called the regularization parameter. Typically, in most scenarios, you don't have a quick way of picking lambda. You have to try different lambdas, okay, to see what works for your scenario, what works for your problem. Okay, so now just to formulaically speaking, we look at this. If A has full column rank, right, then this itself was invertible. But if it is not, okay, if A doesn't have full column rank, or maybe A even is fat, right, in that case A transpose A, you know for sure, will not have full rank, right? It's not invertible. But when you add lambda I, this whole thing is always going to be invertible, okay, provided your regularization parameter is picked carefully. Okay, it's similar to what you had in the last class, right? We had the matrix M, and we wrote down the eigenvalues of the matrix M and so on and so forth. Depending on the choice of lambda, you will actually have this inverse will always exist. In fact, here you can pick any lambda bigger than or equal to 0. okay, because A transpose A will have eigenvalues that are all going to be greater than or equal to 0. So let's say the eigenvalues of A transpose A are like mu1, mu2, so on up to mun. The only issue you have is that these mu1, mu2 may be 0, right? If A transpose A is invertible, they may be 0, right? But when you add lambda I, all these eigenvalues get shifted by lambda. So you get lambda plus mu1, lambda plus mu2, so on up to lambda plus mu1. Okay, so this definitely is going to be above 0. So all these are going to be above 0. So this whole thing is actually going to be a positive definite matrix. Definitely, it's always going to be invertible. Okay, so this inverse will always exist, and this always. So this solution will always be unique. Okay, the solution to Tikhonov regularization will always be unique, regardless of what A is. It could be fat, it could be skinny, whatever. Okay. Okay. In fact, there is a very interesting consequence here. One can actually apparently also take the limit of this as lambda goes to 0, A transpose A plus lambda inverse. We have to be careful about matrix limits. We didn't define them carefully, but you can always actually take the limit of this, right? Because this as you take lambda closer and closer to 0, in fact this will not actually blow up. Okay, and this limit will actually be equal to the pseudo inverse of the matrix. Okay, I'm going to leave the proof, skip the proof, because I think it's going to distract us too much. Proof skipped. Okay, fine. So so that solution for Tikhonov regularization always exists, as I was saying, so this is typically very useful when A is fat, right? Because if A is fat, then Ax equal to B has many solutions. Out of those, I want to pick a solution that has the smallest norm. Okay, but unlike the min norm problem, I'm not very particular about Ax being exactly equal to B. I'm fine with allowing some variation. It's important for me that X is also. Okay, regularization imposes some assumptions and in some sense allows your Ax to be a bit far away from B. Okay, that's why this regularization is also a popular technique to avoid overfitting. Okay, overfitting is a very similar problem that we had in the last we saw very briefly, not in much detail in the last lecture, but regularization is also a very useful technique to avoid overfitting. Okay, I'll not go into much details on that here. Yeah, so as I was saying, if A is fat, so let's M cross N, and let's assume M is much smaller than N, right? It's a fat matrix, right? Then computing this is actually a bit difficult because A transpose A ends up becoming N cross N, okay? And N is the larger dimension here, so this becomes a very large matrix. Okay, and in that case, it's not really clear how we would go about. So this A transpose here is going to be an N cross N matrix. Okay, it's not very clear how we would go about because N could be very, very large, right? So in this context, there is a very useful trick to apply. So one can actually use this result. A transpose A plus lambda I inverse A transpose is equal to A transpose plus lambda I inverse A transpose. Okay, meaning that you could actually change the order here. So A transpose can be brought to the front, which is what you did here, by changing the order of multiplication here. Okay, this result actually follows just by cross multiplying, meaning multiply this term here and multiply this term here. Okay, meaning that A transpose times A transpose plus lambda identity is equal to A transpose A plus lambda I plus A transpose, right? So all I did here is I moved this term over here to the front, I moved this term over here to this place. And this is what you would get, and you can see that this is clearly true, right? Because you have A transpose A transpose, you have A transpose A transpose, same terms on both sides, lambda A transpose, lambda A transpose. Okay, now what does this trick do, right? This trick essentially, this matrix here is N cross N, very large, but this matrix over here is M cross N. So very small, because A is m cross n fat becomes a very small matrix, right? And you are going to now invert a much smaller matrix. Okay, so this is a very useful trick. This is actually it's a precursor to the very popular kernel trick in machine learning, right? The main idea behind kernel trick is when you have large vectors, you can compute their inner products, right? Instead of dealing with large vectors themselves, you just deal with their pairwise inner products, which is roughly what you are trying to do here. You are dealing with the inner products A transpose A instead of the vectors, the large vectors involved in A themselves. Okay. So this is the main idea behind multi-objective least squares. We are not doing this lecture very rigorously. I'm just trying to give a brief outline of what is all involved. The key takeaway is multi-objective least squares can be solved just like least squares, by combining them under a single norm. Okay, and then we introduce Tikhonov regularization. There are other variants of least squares. Some other variants would be non-linear least squares, which I mentioned in the beginning, where under the square each of the terms have some non-linear expression. So we have something like f of x minus f1 of x minus b1, f2 of x minus b2 whole square, so on, right? You're trying to minimize this, where f1, f2 are not necessarily linear expressions in x. Okay, or you could also have, so non-linear least squares are mostly dealt with in different heuristic sort of a level. It's very hard to exactly solve them without knowing more about what f1 and f2 are. Okay, you also have something called constrained least squares, where you're trying to minimize something like some a x minus b whole square, but you have some constraint, meaning something like cx equal to d. Okay. Typical approach to solving this will be explored in more detail in courses on optimization, for example. Okay, so we'll not look at those things here. Okay, so these are many different variants of least squares that come up. Okay, I briefly want to talk about some connection to statistics and estimation. Okay, we don't have that time, and even it's not in the scope of this course to go into much detail, but I just want to give you some very quick overview, right? So what we're trying to do here in many scenarios, we will have some situation like this. For example, in the deblurring problem, we precisely had this scenario where x is unknown. Okay, x is unknown. A is some operator. Okay, typically it's going to be a non-invertible operator. Okay, even if it is square, A may not even be square, in fact, right? A could actually be fat, or A could be skinny, or whatever, right? Depending on the context. So A is some operator. Typically you can assume that it's a known operator. Okay, A is known. Okay, you know what A is. I know x, I don't know x, x is unknown, and v is usually modeled as noise or random. Okay, so there is a specific statistical model for v. So v is a random vector, meaning that each coordinate in v is a random variable. Okay, fine. So you have this scenario, and y is your observed value. Okay, now x is unknown but fixed. X is unknown but fixed. A is fixed, known. V is random. Okay, now your y will be random, of course, right? What you observe will be random and depends on what noise you end up encountering, right? If you get lucky, y will exactly be ax, but if you get unlucky, y could be far from ax. Okay, but maybe the probability of that will be small or something like that. Okay, there is some statistics on v. That's my point. Okay, so the problem of estimation in this context tries to find x, an estimate of x in terms of y. Okay, so estimate x from y. Okay, so we'll write x hat to be some function of y, g of y. So given y, you estimate x. Okay, that's the estimation problem. Okay, so now needless to say here, the estimated value of x will also be random, because y is random. What y you observe dependent on v, it's random, and since this is some function of y, your estimated x hat will also be random. It may not be the true x in all scenarios. Okay, it will be some variation around the truths. Okay, fine. So there are many different models here, right? So then you can ask the question, what is the best possible estimator? Okay, what would be a good estimator for x hat? Okay, so there is a theorem in statistics, a very elementary kind of a theorem. It's called the Gauss-Markov theorem. It tells you that under modest conditions on the noise V and under some modest conditions on the estimator, or under some modest conditions overall, this quantity A transpose A inverse A transpose Y is a very good estimator for X. Okay, you can see it's very similar here. The expression that you get here is again the pseudo inverse, right? Meaning you start with Y and take the pseudo inverse, then more or less you will get something that is close to the original X. Okay, in some sense, so to speak, right? That's the Gauss-Markov theorem. We'll not go into the details, and you can actually have a look at it. It's actually something called BLUE. It's the best linear unbiased estimator. Okay, unpacking that will take some time, so we'll not really do that. Okay, but there are many other scenarios that present with this sort of setup. Okay, for example, something like a communication setup, X could be your transmitted symbol, and A could be like the channel, and V could be the noise, and Y is the received symbol. Okay, in that case, your X transmitted message could actually take on a discrete set of values, right? So it may be that X is unknown, but not completely unknown, in the sense that you know that X belongs to a discrete set. Okay, maybe all the coordinates of X are plus or minus 1. I have that information. I don't know what exactly X is, but I have some information. I know that all the coordinates can be plus or minus 1. Okay, in that case, this is not going to work. This is not going to be a good estimator. There will be other ways to find the correct estimator for X. Okay, so basically what I'm trying to say here is that if you also assume some model on X, okay, so let us say that you assume X is discrete like this, or maybe you can assume that X itself is a random vector. Okay, X itself is a random vector with some distribution. Okay, X itself is a random vector, maybe with a Gaussian distribution, right? Gaussian is easy, but let's say something else, right? It would be even more complicated. And in that case, this may not be, the correct estimator or a good estimator. It may not be a good estimator. I won't say correct. It is some estimator, but it may not be a good estimator for X. Okay, there will be other estimations that you will see. Okay, so the reason I'm pointing it out is many people see this a lot, especially in many COM scenarios, and they'll say, why not just do this, right? Why isn't this good? Well, this isn't good because usually in those scenarios you know more. Okay, there is some additional information about X maybe that you need to incorporate, and this is not doing that. Okay, this is the situation where X is completely unknown, and X can take on any real vector, right? That's that situation. Okay, so I think I will close the least square section here. The last 2 lectures on least squares have been mostly like discussions. We didn't do much of heavy theory that we did in the other lectures, so I just want you to get the brief idea from the last 2 lectures, right? Okay, fine. We'll next lectures will be on some other topics in linear algebra.